Okay, in this one, we're given a function explicitly as a polynomial, and we're given that the domain of the function is only between 0 and 9. It's a closed interval, and the function is continuous. And we're going to be asking, where does the absolute maximum occur? Now, we know by the extreme value theorem that if we have a continuous function on a closed interval, there must be an absolute max or an absolute min in that interval. And your candidates where it could occur is at the endpoints, so 0 or 9, or at a critical point. So we have to really determine are 2, 4, and 6 are these one critical points, and if they are critical points, are they actually extreme values that are the absolute maximum? So let's get over back to my pen and paper, so we can look at the critical points for this function. So first of all, if we take the derivative, we get x squared minus 8x plus 12. At this point, we can actually take the values that they're given to us in the problem, x equal to 2, 4, and 6, and see which ones are critical points. Because it can't have 3, since this is a quadratic, it only could have at most 2 real roots. And so if I try to figure out where this is equal to 0, notice that it factors quite nicely as x plus 6, x minus 6, and x minus 2. So that says I have critical points at x equal to 6 and at x equal to 2. So that immediately eliminates possibility of answer C because x equal to 4 is not a critical point. So we can classify if we want, or we can just make a table of candidates and just evaluate the function at your 4 potential values. We have 0, 2, 6, 9. These are all values, and we're just trying to see where the absolute maximum occurs, so which the biggest one. So we're just going to take 0, plug it into the function, we get minus 5. You plug into, we have to do some mathematics here, but 8/3. So let's plug 8/3. You have minus, you have 4 minus 16. Looks like plus 24 and minus 5. And so if I have minus 16 and minus 5, that's a minus 21. This is plus 3. So right now that beats out minus 5. I plug in 6. Boy, you get 6 cubed. That's pretty dang big. You get 1/3 6 cubed, and then you get 6 squared, so at 36 times 4. And then we have 12 times 6 minus 5. So this turns out to be a number that's bigger than this one, but 9 is going to turn out to be even bigger. Now, one way to recall this without actually doing through the arithmetic is 2 things. One, we recognize we have an odd degree polynomial, positive leading coefficient, so we know the end behavior is down and up. So we know that as x gets bigger and bigger, eventually it's going to start increasing very, very fast and also get very, very large. We notice that the critical points are at x equal to 2 and 6. So whatever my graph is doing, this is probably a bad picture, but the graph's going to do something like this. And here's the x equal to 2 case, and here's the x equal to 6. 2, and here's 6. So it actually turns out that this value is actually going to be a little bit less than that. So if 9 is over here, we just have to make sure that 9 is greater than that value of 2. But we already determined it was negative. And so we just have to make sure that that value is positive. And so it turns out it is. So we can conclude that x equal to 9 is going to be where the location of the absolute maximum.